Let's be honest, we're surrounded by teams of autonomous robots. They're already coordinating satellites, managing entire fleets of delivery drones, and yeah, they're going to be driving our cars in perfect formation one day. But making sure these teams are reliable, that's one of the biggest, toughest challenges in modern engineering. So, what happens when one of them goes rogue? Just picture it, a massive swarm of satellites, all working together in perfect sync. And then, suddenly, one of them has a tiny, almost unnoticeable malfunction. In a team that's so tightly connected, that single tiny error can set off a catastrophic domino effect and put the whole mission at risk. The stakes are just incredibly high. Now, the technical name for these robot teams is a multi-agent system, or MAS for short. And this isn't some far-off science fiction. They are the backbone of logistics, of exploration, of the communication systems we already depend on every single day. And as we rely on them more and more, our need to trust them, well, it has to be absolute. There's a quote from the source research that just hits the nail on the head. It says, "The malfunction of a single unit can be transmitted." Think about that. A fault isn't just a breakdown. It's more like a virus that can spread through the whole network, making the entire team sick. One bad agent can tank the whole mission.
Okay, so we get the risk. It's a big deal. The real question is, how do you find that one faulty agent before it's too late? How do you even begin to find the glitch in the system?
Well, here's where it gets really, really tricky. These systems are operating out in the real world, which is noisy and chaotic. For a satellite, that noise could be solar radiation messing with its sensors. For a fleet of cars, maybe it's a bumpy road or just terrible weather. Trying to hear the tiny whisper of one component failing inside all that chaos, it's literally like trying to hear a pin drop in the middle of a hurricane. The scientific field that's dedicated to solving this is called fault diagnosis, and it's basically a three-step process. First, you have to detect that there's even a problem. Then you isolate it, figuring out which specific agent is the source. And finally, you identify what exactly is wrong. This analogy just explains the whole dilemma perfectly. Imagine you're a conductor. You've got a single violin that's just a tiny bit out of tune. That's the fault. But you're trying to hear it during this massive symphony with the whole crowd cheering and roaring. That roar, that's the external disturbance. So how on earth do you pick out that one single bad note? Well, if you want to hear that one violin, you need some seriously sophisticated listening equipment. And that's pretty much exactly what researchers Barzegar and Rahimi have built, a kind of noise-canceling headphone, but for robot teams. Okay, now the technical name is a bit of a mouthful. It's an unknown input observer with an adjustable parameter. But hey, don't worry about the jargon. What this thing actually does is surprisingly intuitive once you break it down. So here's how it works. First, the unknown input observer part acts just like noise-canceling headphones. It filters out all that predictable background noise. Once that chaos is gone, it can listen very carefully for the specific signature of a fault. But here's the secret sauce, the adjustable parameter. Think of it like a fine-tuning knob that lets the system zero in on that fault with just incredible precision. So that's the theory. It sounds great, right? But does it actually work? Well, to prove it, the researchers set up this really rigorous virtual mission using a swarm of communication satellites. All right, here's the mission setup. We've got 5 satellites split into 2 clusters. Agents 1, 3, and 5, the ones in green, they're all healthy. But agents 2 and 4, in red, they're about to have a problem. And what's really crucial here is that only Agent 1 is equipped with this new diagnostic tool. It's basically the team's doctor. And believe me, this was no easy test. The 2 clusters were deliberately put in different virtual environments, which means they were getting hit with totally different kinds of background noise. Then, the researchers injected these complex, constantly changing faults into the actuators of satellites 2 and 4, just to see if Agent 1 could figure out what was going on from all the way over there. And right here is where we see it in action. This graph shows what are called residuals. You can just think of it as the system's alarm. As long as those lines are sitting right at 0, everything is A-OK. But then look at those huge spikes. The orange line for Agent 2 and the blue one for Agent 4. Those are the alarm bells, showing that Agent 1 has definitely detected that something's gone wrong. But, just detecting a problem isn't enough. You've got to identify what it is. On these graphs, the blue line is the actual fault happening in real time. The orange line is Agent 1's estimate of that fault. I mean, look at that. The tracking is nearly perfect. It's not just hearing an alarm bell, it's describing the problem in incredible detail. The results look really impressive, I know, but how do they actually stack up against the methods that were being used before? Well, the numbers tell a pretty staggering story. This graph makes the difference crystal clear. The blue line, that's the real fault. The orange line, that's our new method. And you can see it's tracking it super closely. But now, look at that yellow line. That represents the older standard method. It's really struggling to keep up, right? The errors are just so much bigger. 56.61%. That is the average reduction in the estimation error that this new method achieves compared to the standard approach. That's not just a small improvement. It is a massive leap forward in diagnostic accuracy. And for anyone who loves to see the raw data, here it is. This table shows the root mean square error. Just think of it as a score for how wrong an estimate is. The lower the score, the better. The standard method scored 1.252. The new method? Just 0.5432. The proof is right there in the numbers. So, what's the big takeaway from all of this? Why does a more accurate fault diagnosis tool for a bunch of satellites actually matter to the rest of us? This research gives us a powerful new tool for making the robot teams we all depend on safer, more reliable, and way more resilient. By being able to hear that faint whisper of a fault in the middle of a real-world hurricane of noise, we can finally build systems that we can actually truly trust. And that kind of leaves us with this one last fascinating question. We talk a lot about whether we humans can trust AI. But as these autonomous teams get bigger and more complex, the real challenge might be designing systems that can diagnose, heal, and ultimately trust each other enough to get the job done right.